Okay, well, then without further ado, on to distributions. So today we're discussing a couple more types of distributions, specifically the geometric and negative binomial distributions. Then we'll switch to continuous distributions and discuss the uniform and exponential. A lot of these I've at least alluded to earlier in class, but today we'll be discussing them in more detail. So, geometric distribution, we've discussed this a bit. In fact, I mean, there was at least one exam problem where this came in handy, actually two, come to think of it. But just to lay it down formally, that the idea behind a geometric distribution is, say you have a sequence of independent Bernoulli trials. Bernoulli trial, you can think of it as just like a generalization of a coin toss, that there's some event with a probability of success p and probability of failure 1 minus p, and we want to, well, there's a couple things we might want to do. When we simply do a Bernoulli trial fixed number of times and count the number of successes, that would be a binomial distribution. A geometric distribution is a slightly different scenario where rather than doing it a fixed number of times and counting the number of successes, the geometric distribution is you do it over and over again until you get the first success. So, for example, if you flipped a coin 10 times, counted the number of heads, that would be a binomial distribution. If, on the other hand, you flipped a coin until you got a heads and then stopped and counted how many times you had to flip the coin until you got the first head, that would be a geometric distribution. So, sample space, obviously all natural numbers 1, 2, 3, up to infinity, that you have to flip the coin at least once before you get your head. But in principle, you could flip your coin 10 million times before you get a first head. So potential sample space is all natural numbers. This is in contrast to the binomial, where there's a fixed number of trials and you're going to have that same number of trials no matter what. Probability mass function, easy to calculate using the rules of probability. In fact, so far most people calculated this successfully on the exam, even though I never really gave you this formula. But if the probability of success is p, probability of failure is 1 minus p, you have to get x minus 1 successes, 1 minus p to the x minus 1 power times the probability of the single, or 1 minus p, x minus 1 failures with probability 1 minus p, and then 1 success with probability p. So the probability comes out to be p times 1 minus p to the x minus 1 power. And cumulative distribution function, also fairly easy to calculate, is just 1 minus p to the x power. This is the same sort of logic that we used with the birthday problem, if you remember back a couple weeks. The easiest way to calculate this CDF is to consider the alternative that it takes more than x tries to get your first success. And for that to happen, your first x trials have to be failures. Probability of that is 1 minus p to the x, so the probability that your first success is in less than x trials is going to be 1 minus that probability, 1 minus p to the x. And if you want to do some math that I won't bore you with, you can calculate the expected value and variance of this distribution. Expected value is 1 over p, the variance is 1 minus p over p squared. And one interesting property of the geometric distribution is what's known as the memoryless property, that the intuitive way to think about it is that the distribution has no memory, that formally, if you write it down, it says the probability of going k trials before you get a success, given that you've gone I trials, is just equal to the probability of going more than k minus I trials. If you think of it in terms of, another way to think of it is if the lifespan of, say, a light bulb is memoryless, the probability the light bulb lasts another 5 months, given that it's lasted 10 months, is just the probability of lasting 5 months if it were brand new. The fact that it's already lasted 10 months doesn't tell you anything about the probability that it will last another 5 months. And if you take a coin tossing example, given that they're independent, that should hopefully make intuitive sense, that the probability of, if you flip 5 tails in a row, the probability that you have to go 5 turns before you get a heads is exactly the same as what it would have been if you wanted to calculate the probability of it taking 5 turns to get a heads from the beginning of the trial. The fact that you've got X number of failures initially doesn't tell you anything about when you're going to get your next head. And proving this mathematically is easy. If you'll recall the formula from the CDF, the probability that it's more than k trials before you get your first success is 1 minus p to the k. The probability that it's more than I trials where you get your first success is 1 minus p to the I. Using the formula for conditional probability, it's 1 minus p to the k over 1 minus p to the I, which of course is 1 minus p to the k minus I, which is precisely the probability that x is greater than k minus I. And interesting factoid here is that the converse for this statement is actually true as well, that you can prove that if x is a discrete distribution that has this memoryless property, then it must be a geometric distribution. I won't bother to prove that now. Maybe it'll show up on the homework or something if I'm feeling particularly mean, but so, like I said, the intuition is that if x is the number of years that you live, the probability that you will survive 2 more years, given that you've survived to a certain age, is just the probability of surviving 2 more years generally. This, for humans, this is clearly not a very good assumption, that the probability that I survive 2 more years is probably drastically higher than the probability that my 96-year-old grandmother will survive 2 more years. But that's the intuition behind it. So, just as a little note, because this can be confusing if you read papers or other textbooks or so forth, that the way the geometric distribution is defined is not standard across textbooks, that some people, the way I just defined it, which I believe is also the way that Cassell and Berger define it, is that it counts the number of trials until you get the first success. But some including, not saying this well, that say you flip the coin 4 times and get tails, then you get a heads on the 5th time. The way I've defined it, which I believe is the way Cassell and Berger defines it, is the geometric distribution would be, the value of the geometric random variable would be 5 in that case, because it would be the trial where you get your first success. Some books define it as the number of trials before the first success, so they would say that it's 4 in that case. The value of the random variable is 4 in that case rather than 5, and that would mean that the support of the random variable is 0 to infinity rather than 1 to infinity, because if you get a heads on the first trial, then there would be 0 failures before the first success. And these two formulations are completely equivalent, but you need to make sure you read carefully in whatever book or paper you're reading to see how they define it, because it changes the moments and the moment generating functions and a few things like that. If you're not expecting it, you can stare at the paper and be like, what? Why is that? Oh, they parameterized it differently. So just word of caution. So, example of a negative binomial distribution. Say you're doing a study on human fertility research and you want to...
Hi, is the Poisson distribution also random?
No. The exponential distribution is, but the Poisson is not. In fact, we'll be discussing exponential here in a second, but if I'm remembering correctly, that's another theorem that geometric and exponential are the only two memoryless distributions, period. That a discrete memoryless distribution has to be geometric, and a continuous memoryless distribution has to be exponential. You may have to add some conditions for those statements to be correct. I forget the exact theorems, but there's some theorem to that effect that I'd have to look up exactly. But one way or another, an example of this is in some studies on human fertility. There's sometimes epidemiologists are interested in what can increase the amount of time it takes for a couple to conceive or decrease or whatever. So let's say we believe the baseline probability of conception in a given month is 0.25. What would be the probability of conception in the third cycle? Well, I won't even ask you to try to calculate because it's fairly straightforward. You just plug in the numbers. 0.25 times 1 minus 0.25 squared ends up with a probability of about 0.14. And if you wanted to calculate the expected number of cycles to pregnancy, well, remember that the expected value is just 1 over p. So in this case, it would be 1 over 0.25 or 4 months. And what would be the probability of not becoming pregnant within 12 cycles, which is the definition of clinical infertility? Well, that would be the probability of... Actually, now that I think about it, I probably should have... No, I guess this is right. Be the probability that you get 12 failures in a row, which is 0.75 to the 12th power, or about 0.032. Well, hopefully that's fairly straightforward. Let me know if anybody has any questions thus far. Okay. Negative binomial distribution is related to the geometric distribution, but it's a bit more generalized. That it's the same idea that you have a series of Bernoulli trials that you repeat until you get a success. But the difference is for the geometric distribution, you kept going till you got one success, one heads, as it were. The negative binomial distribution is you keep going until you get S successes. Say you stop once you get your third head rather than getting the first head. So sample space in this case would go from S to S plus 1, S plus 2, etc. You have to get at least S successes. So if the first S trials are all successes, then you could stop on trial number S, but you can never have less than S trials, and if you get some failures mixed in there, then you'll stop sooner. And probability mass function, again, this is something that you've calculated, I think, on both homeworks and exams by now, and most of you did it correctly, but is that it's similar to the idea for the geometric distribution that you have to get S successes with probability P to the S and X minus S failures with probability Q, which is equal to 1 minus P. I probably should have written that somewhere, to the X minus S. But this is slightly more complicated because with the geometric distribution, there was only one possible order that this could happen. That you had to get X minus 1 failures followed by 1 success. That's the only possible order there. But when we have the negative binomial distribution, there can be various possible orders of the S successes before you get the S successes over the X trials, that you do know that the last trial has to be a success, because once you get to S successes, you stop. However, in the X minus 1 trials before the final trial, they can happen in any order you want. Let's say that we're flipping a coin until we get 3 heads, and we end up getting our third heads after 8 trials. Well, you could have 2 heads on tosses 1 and 2, followed by 5 tails, followed by 1 heads, or you could go heads, tails, heads, etc., etc. There's all these different possible orders for the first S minus 1 successes before you get the final S successes. In particular, there's going to be X minus 1 trials before trial number X where you get the final success, and there's going to be a total of S minus 1 successes among those X minus 1 trials. The total number of possible orderings of S minus 1 successes and X minus 1 trials is, of course, just X minus 1 choose S minus 1. So the total probability that it takes X trials to get S successes is going to be X minus 1 choose S minus 1 times P to the power S times 1 minus P to the power X minus S. That makes sense. Everybody's seen enough combinatorics that this is relatively old hat by now. Okay. And there's no simple form for the CDF of the negative binomial distribution. If you need to calculate it, in an exam in this class or a qualifying exam, probably your only option is just to write down the summation, because calculating it by hand would be a really miserable experience. If in the real world where you're not taking an exam, you can just use R or something like that. And you can also show the expected value in this case is S divided by P. Again, this should hopefully make intuitive sense that if the probability of success is P, then you would expect to go 1 over P trials on average before you get your first success. So to get S successes, you would expect to be S times 1 over P. The variance will be S times 1 over P squared. So if you're curious why on earth they call it the negative binomial distribution, there's a story in Cassell and Berger that I won't go into, and if I'm being completely honest, I didn't even bother to look it up myself. But can also show very easily that a negative binomial distribution where you go for one success, you go the number of turns until you get one success, of course, just a geometric distribution, which is by definition a distribution where you keep going until you get a single success. And you can also show that you can get a negative binomial distribution just by taking the sum of n geometric random variables. Again, that makes intuitive sense that geometric distribution is the number of trials that it takes to get one success. So if you count the number of trials it takes, and also taking into account that it's memoryless, number of trials it takes to get the first success, the number of trials it takes to get the second success, the number of trials it takes to get the third success, well, that's the very definition of the negative binomial distribution. And also worth pointing out that if you have a sequence of successes and failures or something like that, just by looking at that sequence, there's no way to know if it was generated from a negative binomial or from a binomial distribution where we do 10 fixed trials, or a negative binomial where we stop after we get 6 trials. You need to know the experimental design to compute the probabilities. Now, if you got a sequence like this, the last one were a failure, you would know that it has to be binomial, because if the last one were a failure and it was a negative binomial, then you should keep going. But for the outcome that we've listed there, there's no way to tell one way or another. So Example of negative binomial sampling, say that a proportion P of the population has a certain disease. How many people would you expect to have to sample to collect R with the characteristic? And we're going to assume that this is essentially like sampling with replacement. I mean, theoretically, this doesn't really have a negative binomial distribution because you pull someone out of the population with the disease and then you reduce, since we're not sampling with replacement, that reduces the probability that the next person has the disease by some tiny amount. So maybe you should theoretically be using hypergeometric rather than negative binomial. In practice, if you're sampling from a huge population, it's not going to make a difference. But expected value in this case, of course, would be R over P, just the expected value of the negative binomial. And how many people should we sample in order to be 95% certain of getting R people with the characteristic? Well, as I said before, the only good way to do that is to use R. I mean, I guess I could have written the summation on the board, but if you were expecting math, you're going to be disappointed today because that's the closest you can get to an exact calculation for that. And once again, quick note that there are some books that define negative binomial as the number of failures before the S is success. This is equal to the previous definition. I don't think it's minus S, I think it's minus 1 actually, but yeah, that, or well, anyway. In that case, no, I guess, yeah, it is, would be minus S, sorry. But in this case, we don't count successes at all. We only count the number of failures. I mean, I think there are other books that count another way, but whatever. For the sake of this discussion, in this case, the sample space would be going 0, 1, 2, up to infinity because it's possible that you get no failures before success number S, or you get 1, etc., and you would, and the PMF would be S plus X minus 1, choose X times P to the S times Q to the X. In my experience, that particular formulation is not common. I think I've seen it before, but the one that I just described is far and away more common. Geometric, every book does it differently. About half do it the way Cassell and Berger does. About half seem to do it the other way. So that's where it's a bigger issue. But just in case you ever see this formulation of the negative binomial distribution, that's what it looks like. And negative binomial distribution you can sometimes use for modeling count data as an alternative to the Poisson distribution. That, as you'll recall, the usual intuition for the Poisson distribution is a certain event happens with a certain rate. So let's say that we define this event happening to be a success in a series of trials, and we want to count like how long we have to go until we get S successes. Well, what if we define the probability of success in our negative binomial distribution to be S over S plus lambda? On the next slide, I'll explain why we chose that particular value of P. But then, if you work through the math, you can show the negative binomial distribution with probability of success P will have an expected value of lambda and a variance of lambda plus lambda squared over S. Is there a question, or were you just stretching? Okay. And the reason we might want to do this is that, as you'll recall, the Poisson distribution, the variance equals the mean. And sometimes when you're modeling count data, that assumption is not going to be satisfied, that sometimes the sometimes the rate at which, if you look at the distribution of the amount of time before an event happens under what you think should have a Poisson distribution, it will have much greater variance than just lambda. The negative binomial distribution, as you can see here, its variance will be greater than simply lambda, so you can take into account the fact that the physical phenomena you're modeling may have greater variance than would be predicted under the Poisson distribution. I don't know if you've ever been exposed to this idea of overdispersion in any of your other classes, which basically means that you fit a model to the data, the model specifies that your data should have variance of a certain level, and the data and the variance in your data is actually greater than that. If you haven't seen this before, I'm sure you'll learn it at some point in 663 or 762, or I honestly don't know where they teach this in our curriculum, but I'm sure we teach it somewhere. But for the time being, the important point is that the negative binomial distribution can be used to model the Poisson distribution with higher variance. That, I mean, off the top of my head, I know one place that this is used is if there's anyone in here who's ever studied biology and knows anything about RNA-seq data, which is used to measure expression levels of proteins in genes, that I'm not that familiar with the technology nor with the statistics used to analyze this type of data, but I know the basic idea behind it is that the number of copies of the protein produced should have some rate-like distribution that can be modeled using Poisson or negative binomial, and if the variance in the data is too high, that's a reason to use negative binomial. And I wish I knew this stuff better so that I could tie this to the real world a little better, but this is a big research area in statistics right now, so if this type of thing interests you at all, that is one thing that makes it worthwhile to know something about the Poisson and negative binomial distributions besides just passing qualifying exams. Anyway, so if we define the Poisson distribution the way I did on the previous slide, and this is again using the alternative parameterization where we're counting the number of failures before you get S successes. If you write out that particular formula for the PMF, that's of course going to be S plus X minus 1 factorial, X factorial, S minus 1 factorial, times S over S plus lambda to the S power times lambda over S plus lambda to the X power, which of course we can write as lambda over X factorial times this piece here plus 1 plus lambda over S to the minus S power. Well, as S gets larger, this piece in the middle is, you end up with like S to the power X over S to the power X. The denominator, using L'Hopital's rule or whatever, you can see that piece goes to 1, so you end up with lambda dx over X factorial times this thing, which if you recall from calculus, the limit of that thing goes to e to the minus lambda. Get lambda dx over X factorial times e to the minus lambda, which is of course precisely the PMF of the Poisson distribution. In other words, if we take a negative binomial distribution, let P equal the value that I laid out on the previous slide, and we get that for large S, this distribution will converge to a Poisson distribution. So, punchline, the negative binomial distribution can be approximated by a Poisson distribution with the appropriate parameterization.
So,
Right. So now we'll shift over to continuous random variables, starting with the simplest one, uniform distribution, which the intuition is you're choosing a random number somewhere between 0 and 1. It's equally likely to be any number between 0 and 1. And its PDF is quite simple. It's just 1 on the interval from 0 to 1. Easy to see that that integrates to 1. And again, agrees with our intuition. Since it's constant everywhere, it's equally likely to be any value in that interval. And CDF we get just by integrating from minus infinity to y, which is equivalent to integrating from 0 to y, given that the PDF is 0 for y less than 0, and we just end up with the CDF being equal to 0 for y less than or equal to 0, y for y between 0 and 1 for y greater than 1. And you can generalize this to a uniform distribution on A to B. Sample space obviously goes from A to B. It's equally likely to be any number between A and B. The PDF is going to be 1 over B minus A for y in that interval, 0 elsewhere. I can already hear you saying that would have been useful to know before the exam, Eric, but most of you got that one right anyway. And to calculate the CDF of that, you just integrate it and end up with y minus a over b minus a in the interval from a to b, 0 below that interval and 1 above that interval. And also, taking some not too complicated intervals, you can show the expected value is a plus b over 2. Again, that makes intuitive sense that if it's equally likely to be any value in the interval, its expected value should be the midpoint of the interval. And its variance turns out to be b minus a squared over 12. And uniform extends the continuous case, the idea of equally likely outcomes. It's equally likely to be any number in that interval. It's also pretty easy to show that if you have a uniform 0, 1 random variable and you add a and then multiply it by b minus a times y, then you get something that's uniform on the interval a to b. This is useful mainly if you're doing like computer programming and your random number generator will only generate random numbers between 0 and 1. You can do that transformation to create random numbers that are uniform on any interval that you want. And it can be useful for situations where people arrive at a destination or enter a study or whatever randomly over time. Like, for instance, say there's a bus that leaves every 10 minutes and you arrive at the bus stop according to a uniform distribution between 7 and 7:30. What's the probability you have to wait more than 5 minutes or more than 2 minutes? Well, hopefully that's intuitively obvious. This is going to be 0.5 or 0.8. Probability you have to wait more than 5 minutes is going to be equivalent to the probability that you show up in the interval 7:05 to 7:10 or 7:15 to 7:20 or 7:25 to 7:30. In other words, a 15-minute block out of this possible 30 minutes, so the probability of that happening is 0.5. Similarly, the probability that you wait more than 2 minutes is, I think I actually just said the first one backwards, but you get the idea. Probability that you wait more than 2 minutes is that you do not show up between like 7:08 to 7:10 or 7:18 to 7:20 or 7:28 to 7:30. Oh, add up those probabilities and it will be 0.8. Next continuous distribution that we're going to discuss is the exponential distribution. which is denoted by x exp of lambda. Sample space is all non-negative real numbers. And the PDF, I think we've talked about this a time or two before, is defined to be lambda times e to the minus lambda y for y greater than or equal to 0, and 0 for y less than 0. If you integrate that, you can get the CDF, which turns out to be 1 minus e to the minus lambda y for y positive, again 0 for y negative. The exponential distribution, as an aside, is one of the very few continuous distributions you ever work with that actually has a nice closed form for the CDF. Most continuous distributions, to calculate the CDF, you either have to use a computer or do some sort of numerical integration, because there's no way to do the integral. There's no closed form expression for the integral. And if you do the math and the integrals to calculate the expected value and variance moment generating function, you get the expected value is 1 over lambda, variance is 1 over lambda squared, and the moment generating function will be lambda over lambda minus t. And you can think of the exponential as the waiting time between Poisson events. Said you can the Poisson distribution you can think of as an event happens with some specific rate, and how long, how many, and what is the expected number of events you get in a given time interval given that rate. So let's say the number of events in time interval follows a Poisson distribution with rate parameter lambda. Then the probability that y is greater than some value t is of course equal to the probability that you get no events between time 0 and time t. But the number of events in 0t, if the rate parameter is lambda, then the rate parameter over t time units would just be lambda times t. So the probability that you get 0 events over t units be e to the minus lambda t. So the probability that you get that there's an event before time t is 1 minus e to the minus lambda t, which of course is just the CDF of the exponential distribution. And density, what I just laid out previously. And this is another one of those cases where different books define the exponential distribution in different ways. That some books, rather than defining the exponential rate parameter as lambda, they basically define it as 1 over lambda, so the density becomes 1 over theta e to the minus y over theta. Again, this is completely equivalent to the formulation that I used and that Cassell and Berger used, but if you do it that way, then of course you have to take 1 over lambda in the expected value and variance, so that you get the expected value is equal to theta, and the variance is equal to theta squared. And I'm trying to remember, I think this may be the parameterization that R uses. My memory says that it is, but I would have to look that up. But it's annoying. Every time I mess with the exponential in R, I have to look this up because I can never remember it. But I want to say this is correct. So if you need to compute things using the exponential distribution in R, I think you have to take 1 over the rate parameter used in Cassell and Berger to get R to give you the correct numbers. And the exponential distribution also has the memoryless property that the probability that you survive until time s plus t, given you've survived to time t, is the probability of surviving to time s. That is the probability of living 2 more years given that you've already lived 30 years, is just the probability of surviving 2 more years when you're born. And mathematically, that means the underlying Poisson process is stationary. The rate at which people die is constant and does not change over time. That's clearly not true for humans. Might be true for something like turtles if you want to talk about animals, but most of the time it would involve something like, I don't know, maybe some type of mechanical failure or something like that. I'm not thinking of a lot of good examples right now. I guess something like coin tossing is an obvious example where every event is independent, but anyway. And a couple slight variants of the exponential distribution, which sometimes you'll see and are sometimes useful, that you can define a shifted exponential, which given an exponential distribution, you just add v to it, where v is some real number. Then it's easy to calculate the PDF in this case. You just replace x with y minus v, and the support of this distribution goes from v to infinity rather than 0 to infinity. And, well, I guess I cut out the rest of this slide. You might use this if, I don't know, dumb example, if you wanted to model a scenario like you're modeling the amount of time you wait to get to the you wait for the bus to arrive. You could use this v to model when you get to the bus stop early or you get to the bus stop late or something like that. But my experience, this isn't used super commonly, but it's useful to know what it is just in case you ever see it. There's another distribution called double exponential, which you get by reflecting the exponential distribution around 0. That it looks just like the PDF for the exponential distribution, except you replace x with absolute value of x and then multiply the whole thing by 1/2 so that it still integrates to 1. I mean, given the positive half integrates to 1, the negative half integrates to 1, the whole thing would integrate to 2. Well, you divide by 1/2 and then you integrate to 1. And if you take this double exponential distribution and set lambda equal 1 and then do a transformation like sigma x plus mu, which again you can think of it as like you were shifting a normal distribution to have mean mu and variance sigma, then you end up with what's called the Laplace distribution, which again, fairly easy to show using the formula from a week or two ago, that its distribution is going to look like 1 over 2 sigma times e to the minus y minus mu over sigma. And you can compute that its variance is mu, or its expected value is mu, and its variance is 2 sigma squared. It's sometimes useful if you want to see how a particular method or particular estimate or whatever performs given data that's non-normal because it has tails that are too heavy to be normal. You don't want to do something with obscenely heavy tails like the Cauchy distribution. As you'll recall, Cauchy distribution has infinite variance, doesn't even have an expected value because its tails are so large that you take the mean of 1,000 Cauchy variables and it's still just a Cauchy. It's not anywhere closer to the center at all. The Laplace distribution has heavier tails than the normal distribution, but nowhere near as heavy as the Cauchy distribution. It actually has a mean and variance that are finite, and all of its other moments exist, so it lets you model data that has somewhat heavier tails than a normal, but not something really crazy like the Cauchy. And that's really all I have to say about these distributions today. It actually took longer than I thought it was going to be. Any questions about any of this? For the 690 students, like I said, I kind of prepared a few things about big O notation, L'Hopital's rule, and Taylor series that there may be a homework problem or two about. If you want to stay a few minutes to talk about it, if you already know this stuff and want to take off, I won't be offended. And otherwise, I hope to have all the exams graded by Tuesday.